Assalamu alaikum. So in the previous lecture, we discussed the modeling for the most common DC machine, which is the separately excited, the shunt, the series, the compound. Now we have also another type of the DC machine, which is the permanent magnet DC machine. In the permanent magnet DC machine, it's actually in the same fashion as separately excited DC machine, except that we don't have any coil in the IDS. So simply we will end up with only one equation in the direction of the QR. So this is what I need also to recover here, which is the parent magnet DC machine. Now this is identical to the separately excited DC machine, except that we don't have a field winding. So if we writing the equation, it only will have a single equation, which is the V QR will equal to R QR plus I QR plus L QR d I QR by dt plus we having lambda m multiplied by omega r. And this lambda m is constant and all the time is pointing toward the dx. So if I need to plot it here, the configuration, it will be something like this. Lambda m here, and only we have one coil and one current. So in the same fashion as the parent magnet AC machine, this type of the machine is high efficient. Why? Because we don't have any winding, any actual winding here in the stator. So there's no copper losses, which means that this machine is high efficient machine. Now in terms of the machine variable, we can write it as the voltage equation VA is equal to RA IA plus LA DIA by dt plus the back EMF here, and the back EMF is proportional with omega r, and lambda m is constant. This one is constant. So simply here we can say EA is equal KA omega r. So in the same fashion, the parent magnet DC machine can be seen as an armature controlled separately excited DC machine. This is the first point I need to highlight. The second point I need to highlight, the position of the brushes. Now, in general, we are placing the brushes in the, what we call it, in the magnetic neutral axe. Now this actually is the magnetic neutral axe. Neutral axe. Now, if we have an armature reaction, which means that the current in the armature is producing a flux that weakens the main flux. In this case, sometimes we will shift the axe of the brushes in order to eliminate the armature reaction. So this will be your task. This will be the separately excited DC machine with shifted brushes X. The point. Now let's assume that this is the rotor. Now this is the magnetic neutral axe. Now the field is here. So let's assume we are connecting plus minus V ds. This should be the I ds. Now let's assume that the brushes is shifted to this point, for example. Now in this case, virtually, I will have two coils. The first coil will be here, and the second coil will be here. So this will be the DR coil, and this will be the QR coil. And this angle, let's say it is beta. So simply, now I dr is not equal to 0. It has a component. So I dr will equal IA cosine beta, and IQR will equal IA sine beta. Still, we having the IDS is equal to IF. So what I need you to do is to find also the mathematical model in order to find the effect of the shifted brushes here. And this will be lifted for you as an exercise. So now let's continue with the torque speed characteristic for the DC machine. Now, if we record the separately excited DC machine, and if we need to find the torque speed characteristic, let's record the armature controlled DC machine where the flux is constant, or simply the parent magnet DC machine. We having the VA is equal to IA RA plus LA DIA by dt plus certain constant. Let's assume this one is K phi omega. Now at steady state, which means that all the variables are constant, so d by dt will go to 0. We will end up with VA is equal to IA RA IA plus K phi omega. If we solve this equation with respect to omega, so omega will equal VA over K phi minus IA RA over K phi. Now, also, the torque is proportional with IA, so the torque is equal K phi IA. So simply here we can write also omega as VA over K phi minus RA over K phi squared T. Now this is called the electromechanical characteristic, the relation between the current and the speed, and this is the torque speed characteristic, the relation between the torque and the speed. It's the same because the torque is proportional with the current. Now if we are trying to plot it, simply we will find that omega will equal omega 0, what we call it the no load speed, minus delta omega. Now from here, omega naught depend on the flux and the armature voltage, which will equal VA over K phi, while the drop voltage or the slope depend on the resistance and the flux. So this one is equal to RA over K phi IA, or simply it's also equal to RA over K phi square T. So if we need to plot the torque speed characteristic for the armature controlled separately excited DC machine, so let's assume that we are plotting the torque speed characteristic omega. The first thing here, we will have the no load speed omega naught, which will equal to VA over K phi, and remember here the flux is constant because we are assuming armature controlled or a pair of magnet, and after that we having slope due to the reduction, and the slope here is equal to R over K phi square. Now this line for certain voltage. So how to control the speed of the machine? Now to control the speed of the machine, the first thing why we need to control, let's assume that we're having a load torque, which is constant load. So this point here is the steady state point. Or the operation point. So at this point, the machine will rotate at certain speed, let's assume omega 1. Now let's assume for any reason we need to operate at speed, let's say less than omega 1. Let's assume that we need to operate at this speed. So what we can do, we need to control the speed of the machine. Now to control the speed of the machine, if we look here, now we can control the speed of the machine by controlling the voltage, or by adding resistance in series with the armature, which actually can be seen as a voltage control because we are dividing the voltage, or simply by controlling the flux. Or by controlling the flux, we cannot control the torque because the torque, we cannot specify certain torque. The torque depends on the load. This is the point here when TE is equal to TL. So we cannot control the load torque in order to achieve the speed, because in general the load torque must satisfy certain speed profile, and we must fulfill that. So looking for the speed relation here, we can say that we have three possible methods to control the speed. So here we have three possible methods to control the speed. The first one is the armature voltage, VA control. And if VA control, we can changing VA from 0 to VA rated. We cannot impose a voltage more than the rated because of the insulation of the windings. And here the speed can be controlled from 0 to the omega base, let's say. The second method is adding resistance in series, adding R external in series with the armature. Now, simply this one is not recommended because adding resistance, the efficiency will be very poor. So this one is not recommended. And finally, we can use the field or the flux control. But again, in the same fashion we discussed the V over F, the speed omega is proportional inversely with 1 over the flux. So the only possible scenario is to reduce the flux because increasing the flux is not possible in physics due to the saturation in the core. So the only possible scenario is to reduce the flux, so the speed will be increased, but simply we should maintain the power constant, which means that the torque will be reduced. So if we plot here the torque speed characteristic, and this is omega for different speed, let's assume this is what the base speed. This will be parallel line for the voltage control. Why parallel? Because simply we are not changing the slope, only we are changing the no load speed. And this one here we'll call T start. Now if we have a load, let's assume this load is constant, then according to the V, if this one V1, V2, V3, V4, such that V1 greater than V2 greater than V3 greater than V4, we have different speed. Now for this is what we call the VA control, which we can achieve a constant torque. While in the flux control, we cannot maintain the slope because the slope depends on the flux. So simply this means that in the flux control we'll have something like this for certain fluxes. So this is the flux control. Now, in the flux control, we know that the torque is proportional with IA and IF. So this means that it's proportional with the flux and the IA. So in order to achieve maximum torque capability, so for maximum torque capability, IA should be IA max, the maximum current allowed in the armature. And in principle, the power developed will equal EA multiplied by IA. So this will equal K phi omega multiplied by IA. This must be constant for omega greater than omega base. So let's assume the maximum current is the rated current here. So this is the case that I will discuss here. So let IA is equal IA rated. So in per unit, IA in per unit will equal to 1. And remember that if I need to calculate any function in per unit, so the function in per unit will equal the actual function over the base function. And sometimes we have the actual over the rated. So now I will plot for IA equal 1 per unit. So this is omega also in per unit. And because the current is 1 per unit, then omega base will equal to 1 per unit. And the voltage will be increased, and the back EMF will increase until it reach its maximum value, E A max. And because we are using 1 per unit, then the power developed and EA will be the same, because this one is 1 per unit, so the power in per unit and the back EMF in per unit is the same. So this is the plot of EA and the power developed. After that, it will be constant until we are reaching omega max. This will be omega max, and this one depends on the mechanical structure and the mechanical design, how much vibration the shaft can handle. Now the torque, the torque, here we can write that the torque is proportional with IA and the flux, and because IA is 1 per unit, simply this means that the torque in per unit is equal the flux in per unit. This is only because we are selecting the current to be 1 per unit. Now, for the torque and the flux from 0 speed to the base speed, let's say, omega base here, the flux must be constant and the torque will be constant. That's why this one we call it the constant torque region. And after that, the flux will be reduced, the flux will be weakening, so the torque will be weakening. And here the power must be constant. The power must be constant. So we have region number 1 here, and we have region number 2 here. So for region number 1, which is the VA control, this is called the constant torque region. And for region number 2, which is the flux control, this is the constant power region. Now, if I change the current to be 1.5 the rated, or 2 times the rated, in this case, the current in the per unit will be not equal to 1.5 or 2 according to the actual selection of the current. So simply the relation now between the power developed and EA is not equal in per unit, and the same for the flux and the torque. So in this case, I need to plot four curves. Now, in order to let's say control also the machine must be operated in the 4-quadrant operation, because sometimes we need the machine to rotate in the forward direction, sometimes we need to rotate the machine in the reverse direction, and sometimes we need to go from the forward to reverse. Sometimes we'll do the regenerative, or the machine will enter to regenerative braking, or acting as a generator. So simply it's worth to discuss with you the 4-quadrant operation. So here we'll discuss the 4-quadrant operation. And for the 4-quadrant operation, I will ensure that the field is constant. I'm not changing the field, because in the DC machine, or even in any machine, if I need to change the direction of rotation, either I need to change the direction of the field or the direction of the armature here in the DC machine. So for that, I will ensure that the field is constant for constant field. So let's assume this is the torque. Let's assume this is the speed. And we have the first scenario here. This is the machine. And this is EA. Let's assume plus minus. And here is the supply. We are connecting the supply here. Plus minus VA. Here VA is greater than EA, so the current will flow from the high potential to the low potential. So this means that IA is positive, which means that the torque is positive, and EA is positive. So this means that omega is positive. So the power is positive. The power is the multiplication of the torque and the speed. So in this case, we have the forward motoring. Or what we call the Q1 region. Now here, because the speed is positive, then EA is positive. Now still here the voltage is positive, but here EA is greater than VA, so the current will flow from the machine to the supply, and this means that the machine now is acting as a regenerative braking, or is acting as a generator. It's acting as a generator in the forward regenerative braking. So here what we have is that the current is negative, so IA minus VE, which means that torque is minus VE. The speed omega is plus VA, so the power will be minus VE. So the machine here is acting as a generator, or what we call it the forward regenerative braking. And this will be Q number 2. Now, let's assume that the terminal of the supply is reversed. So this will be the plus, this is the minus for VA. And the machine will start to rotate in the opposite direction. This is the opposite direction for the speed. So this is the plus minus EA. Now here, still we have VA as absolute value is greater than EA as absolute value. And here I'm using the absolute value because I'm discussing a relative relation between negative numbers. So in order to respect the mathematics, I must use the absolute value. So omega E is negative. So here omega E is negative. And because the absolute value of VA is greater than the absolute value of EA, the current will flow from the following direction. So now here the current IA is negative, which means that the torque is negative, which means the power will be positive. Now if the power is positive, this means that this machine is acting as a motor, and this will be the reverse motoring. And this is the Q number 3. Finally, here let's assume that still we are imposing a negative voltage to the armature, but the absolute value of EA is greater than the absolute value of VA. Now still the speed is negative, omega E is minus VE, but now the current will flow in this direction, which means that IA is positive, so the torque is positive, so the power will be negative, which means that the machine is acting as a generator, or this we call it regenerative braking, reverse regenerative braking. And this will be Q number 4. Now in order to give you example of the regenerative braking, let's assume that here we're having a car, and the car is climbing up in this direction. Now this will be the direction of the FE. Now here we're having the weight, which has two components. One is orthogonal here, and this will be the F load. And now the rotor or the machine is rotating in this direction. Now let's discuss the following scenario now, that after climbing up, now the machine is driven by, under the effect of the load, so this will be the F load, and now the machine is trying to brake, so this is FE or F, let's use FM maybe, it will be for the motor, and still we are rotating in the same direction. So the regenerative braking is caused by when the load torque is caused the machine to rotate in a speed higher than the rated speed in the same direction of rotation. In this case, the machine will act as a generator, or it will enter to regenerative braking. So here the machine is acting as a motor. Here the machine is acting as a generator. Now another way we can enter to regenerative braking. Now let's assume this is the torque, this the speed, and for certain voltage, for certain load, let's assume it's constant load here, we are operating at this point, at omega 1. And this is, let's say, VA1. Now, for any reason, I need to reduce the speed. So, reducing the speed, this means that I need to go to this voltage. Let's assume that this is the line of the voltage that I will choose in order to operate at this speed. So let's assume that this is the speed that I need to go with, which is correspond to omega 2. So I need to go from 1 to 2. How? By changing the voltage from VA1 to VA2. So how I can do that? Remember, the speed cannot jump, because it's governed by differential equation. JD omega by dt must equal the summation of the torque. And the current, of course, cannot jump, because there's inductance in the machine, and it will be LdI by dt. But if we, let's say, discussed from time scale different point of view, the time constant of the electrical part is much faster than the time constant of the mechanical part. So simply, roughly, we can see that the current is changing rapidly, and the speed still is constant. So simply, those actually are straight lines. Those are parallel lines, by the way. Huh? And in order to go from 1 to 2, automatically, if I change the voltage from 1 to 2, this means that this line now is forbidden, and I should follow this line. So the first thing here, I will go to this point. Do you see now? The load cause the machine to operate at a speed higher than the no load speed in the same direction of rotation. In this case, I'm entering to regenerative braking. After that, the machine will be de-accelerate until we are achieving this point. So in this case, I'm going from 1 to 2, from Q1 to Q2, then back to Q1. So from here to here, I'm dissipating the energy or storing the energy in the inductance. Then from here to here, I'm feeding the energy to supply. Of course, if I need to feed the energy to supply, I must have a mechanism that can handle the power flow, and the supply must accept the energy. So this is also another case for the regenerative braking. Another way for a regenerative braking, imagine that you need to go from Q1 to Q3. You need to go from forward motoring to reverse motoring. In this case, and this is what we call it plugging. This is what we call it plugging. Let's assume that this is the torque speed characteristic for certain voltage VA, and let's assume that the torque is bidirectional torque, which means that the torque all the time oppose my motion or resist my motion, and for any reason I need to reverse the direction of rotation. So I need to go from Q1 to Q3. So if I need to go, I should pass through Q2, which is the forward regenerative braking. Now, if I reverse the voltage, I will get the same line, the parallel line, but simply in the opposite direction here. So this is for minus VA, and also remember that those lines are actually straight lines here. So the first thing, if I need to go from 1 to 2 here, if I maintain the load to be bidirectional, which means the same load, so I need to go from 1 to 2 here. How I can do that? The first thing, changing the voltage. This means that this line is forbidden and I must follow this line. So I will go here to the A point, which can be seen as the torque is jumping while the speed is not. It's because of the time scale. The electrical time constant is much faster than the mechanical time constant. So you can see that the machine is generating huge braking torque. Actually, this is the braking torque, this T braking. After that, the machine will deaccelerate. Here it will cross the zero. Now, if at this point we are disconnecting the load and engaging a mechanical drum, the machine will stop here. If the load is still there, simply the machine will start to accelerate until we are reaching to omega 2, which equal minus omega 1 if I'm maintaining the same voltage and the same load. This is also another method that we will enter to the regenerative braking, which means that in general, if I'm using the machine as a prime mover, as drive, it's not my intention to operate the machine as a generator, but I need the machine to operate as a generator in order to allow the power flow to go from the machine to the supply if there's an extra power, or if there's a generated power in the machine that I can recover. This is also I will go from Q1 to Q3 via Q2. The same thing is applicable if I need to go from Q3 to Q1. So the same thing here, I will follow this line. After that, I will deaccelerate until crossing the zero, then I will accelerate. In this case, I'm going from Q3 to Q1 via Q2. So also, I'm entering to the regenerative braking. So sometime we can use this, let's say, method in order to dynamic brake the machine. So in the dynamic braking, it's similar to the regenerative braking, but the supply is disconnected, and sometimes we are placing external resistance in order to limit the braking current in order to protect the machine. So simply here in the dynamic braking, which is similar to regenerative braking, except that the voltage VA is removed and external resistance, let's say braking resistance RB, is connected with the armature to limit the braking current or the braking torque. So how that can be done? Let's assume that this is the configuration that we have, plus minus VA here. The machine was operating. Plus minus EA. This is the RA. Now this is the switch. Now here we are connecting external resistance, which is RB. And now in the dynamic braking, this switch will go from here to here. So what will happen now? EA is positive, so the current will flow in this direction. This will be the I brake. And here I brake will equal minus K phi omega over the summation of the R. So this is minus EA over R total, let's say, which will equal minus K phi omega over RA plus RB. So here we are using RB in order to limit the braking current. So if we plot the torque speed characteristic here under dynamic braking, this is the torque, this is the speed. Let's assume that this is the torque speed characteristic and I was working at constant load. Let's assume here. And now I need to do dynamic braking. Now the first thing, the voltage is 0, which means that all the lines must cross the 0. So crossing the 0, and the speed or the machine will go following this line until reaching the 0. Now here, if I'm disconnecting the load and engaging mechanical drum, the machine will stop. And this is the idea behind the dynamic braking. Now sometime we can add a resistance, so adding the resistance will change the slope, so we'll end up with different lines here. Which means that we can go either using this path or this path. Now here, let's assume we have 3 cases for the resistance. Let's assume that this is the first one is R1, and this one is R2, and this one here is R3. What's the relation between R1, R2, R3? Which one is the minimum, which one is the maximum? Actually, the maximum braking torque means that the minimum resistance, because in the end of the day the torque will equal minus K phi square omega over RA plus RB. So the minimum R is the maximum current or the maximum torque. So from here, from this plot, we will have that R3 is less than R2 is less than R1. Which path is the fastest? R3 path is the fastest. Then R2 path, then the R3 path. Why? Because simply this is the braking torque in case of R1, the maximum braking torque. This is the maximum braking torque in the case of R2, and this is the maximum braking torque in the case of R3. The higher braking torque, this means that the machine will stop faster. So this will be IB1, this will be the IB2, and this will be the IB3. So next time I will discuss with you how I can change the voltage, either to control the armature or to control the field. Assalamu alaikum. So today, this chair actually is the back.